Okay, I'm going to start the session. I'd like to welcome everyone to the PASS Data Architecture Virtual Chapter. This is our first meeting of the year. Today we have Paul Randal. I'm going to give a talk. And if anyone wants to contact me, my email is rob@sqltigers. I have a blog, www.sqltigers.com. We're going to post the webinar at the PASS virtual chapter site. Also, I'll give a link on my blog to the to this event, this webinar, and I hope everyone enjoys it. So PASS is a great community, a lot of people, and they have a lot of virtual chapters, as you can see. So if you want to get involved and see other great webinars, you can just log in and join these other virtual chapters like PowerShell or Performance, etc. And they always have webinars. It's pretty cool. And here's some great topics. So right now, PASS is going to have a business analytics conference, and they gave me a special code, and it's at the bottom of the screen, BAVCAR. And this code, I was told, will save you $150 off registration. So if you plan on going to the business analytics conference in California in April, it's a quick way to save $150. Use this code, and it'll save you a little money. So yeah, these are some upcoming SQL Saturdays, and you can see PASS is pretty global, and I think everyone knows this by now. They're in Nashville, Cleveland, all over, and it's a great way to get free training from experts in the field. So PASS is also always looking for volunteers. So if you want to volunteer, here's the web link. You can use this link to get to their volunteer site and sign up. And hopefully my computer doesn't freeze up. That doesn't look good. Oh, okay, that's it. So I'm going to change over to Paul's computer right now, and I'm going to let him take over on his presentation. I really want to thank Paul for coming in today and presenting to our group. Thank you, Paul.
You're totally welcome. Okay. So you're seeing everything there?
I see it. If anyone in the audience wants to maybe say they can see okay, that'd be great. Let's see. I'm kind of waiting here for someone to say they can see or not in the chat window. Let's see. I think they can see. I'm not getting any, Oh, yes, tons of people saying to see. I was looking on the wrong plane. I'm sorry. Yeah, a lot of people. Thank y'all for saying you can see. All right, here we go.
Okay, cool. So listen, the way we're going to do questions is every few slides I'll stop and say, are there any questions? And Rob's going to watch the chat window, and he's going to read the questions out to me, and then I'll reply to all of you, okay? And then I'll stay for a question and answer session at the end if we still have some more time. Okay, so thank you all for tuning in to listen. This is a session that I've been doing to lots of user groups, and it's about performance troubleshooting using weight statistics. And I give the same session no matter whether it's a group of developers, a group of DBAs, and a group of architects like you guys are, or aspiring architects. So I'll try to spin this more from an architecture point of view rather than walking up to a SQL server and trying to figure out what's wrong with the system point of view.
Great, thank you.
Okay. So a few little slides about us SQL Skills. We're a bunch of people that do training, consulting, all kinds of stuff like that. You probably know who we are already. There's a list of all the people that work for us. Tim Radney just joined us a couple of weeks ago. Blah, 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 blah. We do lots of classes. We have a bunch of classes coming up in Chicago and Bellevue. Unlikely you guys are going to be going over to London, Dublin, or Sydney, but maybe we've got some international people watching. That'd be cool. There's just an example of some of the performance tuning stuff that we cover and architecture stuff that we cover in our second performance tuning class. If you're interested in any of our classes, go down to the link at the bottom, sqlskills.com/training. A little bit about me. I used to work for Microsoft, blah, 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 blah. So the interesting things about me are our website, sqlskills.com, lots and lots of free information, no marketing, advertising, any of that kind of junk. Our blogs, again, all of us at SQL Skills blog an awful lot. I get no marketing, advertising, just lots and lots of free stuff. And then Twitter, there's a really vibrant SQL Server community on Twitter. It's probably one of the best tech communities that there is on Twitter, and a lot of people, MVPs and people involved in the community are on Twitter as well. And there's also a very cool thing called #SQLHelp. If you have a question and you can pose it in 1 or 2 140-character tweets and add something like #SQLHelp on the end, then a whole bunch of people around the world, including people like me, monitor that, and you'll get some ideas for things to go look at, links to blog posts, white papers, that kind of stuff. Free consulting, you can't beat that. And one thing for you guys, just like Kimberly did in the past fundamentals chapter that she did a couple of weeks ago, we have a lot of training on Pluralsight. It's online training. If you'd like to get a month's worth of completely free access to that, there's no catches. You don't have to give a credit card, nothing at all. There's absolutely no catches, just a free offer for you guys just for tuning in and watching this. Send me an email saying Pluralsight code pass or something like that, and I'll send you a code to be able to get 30 days of access to all of the 120 hours or so of SQL Skills content. More stuff like you're seeing today. All right, so enough of all the marketing stuff. What are we going to be talking about? Weight statistics. So it's very common when people are performance tuning to do what I call knee-jerk performance tuning, where they'll walk up to a SQL Server and they'll see a particular symptom and they'll fixate on that symptom being the actual root cause of a performance problem. And you might think, as data architects, why do you care about this kind of thing? Well, as an architect, you're going to be working with your developers to make sure that the system that you've designed, where it tests, given all the test cases and load testing that you're going to be doing, and also that when it goes into production, it's also working the way that you've designed it to work. And if there's any performance problems, then you're just not going to have the developers go and try and figure out what's going on. You should also be involved in trying to figure out what's going on as well, because it's going to be your design, or mostly your design, that's in effect not working. So this kind of performance analysis that you're going to be doing using weight statistics is also very relevant to you as an architect, because I find a lot of architects are also hands-on coders as well. Maybe they're kind of older developers, are more experienced, and you're not completely divorced from what's going on the SQL Server. So it's really useful for you to have this skill as well. So what we're going to cover today is a little introduction to what weight statistics are. We're going to talk about how the threading lifecycle works inside SQL Server, which is useful for an architect to know. The more you know about how SQL Server works, the better you're going to be able to architect your solutions. We're going to talk about weights and wait times. We'll define those. I'll show you a couple of DMVs that you can use to look at weight statistics, and then I'm going to walk through some of the common weight types and basically some of the common performance problems that you're going to be able to see and diagnose using weight statistics. And I'll do 3 demos for you that's going to show you what's going on. And that's going to take anywhere from 75 to 90 minutes, depending on what kind of questions we get. So as I mentioned earlier, don't assume that the symptom that you're seeing of a performance problem is actually the root cause. Perf troubleshooting, as it says there, is not an exact science. There's all kinds of different things that could cause a particular symptom to manifest. For instance, if you see that a server has high I/O latencies, okay, the kind of knee-jerk reaction to that is, oh, it must be something wrong with the I/O subsystem. It must be some kind of misconfiguration of the I/O subsystem, or the I/O subsystem's gone wrong, or something like that. Now, it's true that if you're seeing high I/O latencies, that's likely because the I/O subsystem is overloaded. But that doesn't mean that there's something wrong with the I/O subsystem. You could have spec'd the I/O subsystem to do a certain number of I/Os, and SQL Server is driving more I/Os than you'd spec'd, and so obviously the I/O subsystem is going to become overloaded. That's not a problem with the I/O subsystem. It's performing exactly as it was spec'd to do. It's something inside SQL Server that's gone wrong. So for instance, there could have been a series of query plan changes, and now what should have been small targeted index seeks are actually doing parallel table scans, and all the information in the tables isn't able to be stored in memory, and so you're essentially having to thrash the buffer pool, the in-memory cache of data file pages, where you're reading some stuff into memory, processing it, and then you're having to throw it away and read more stuff in. So you're having to drive a whole bunch more I/Os because of these incorrect query plans. It could also be, for instance, that the size of the buffer pool has shrunk. You could have a large ad hoc query workload, and you don't have the optimize for ad hoc workloads SP configure option turned on. And so you've got a large number of single-use ad hoc plans taking up space in the plan cache. Now all that memory in the plan cache is borrowed, or the technical term is stolen, from the buffer pool. So more memory that's borrowed from the buffer pool means less memory for storing data file pages, which could mean that you're having to do more I/Os, and so on and so on and so on. There could be all kinds of things that are causing SQL Server to drive more I/O. And that's just one example of a particular symptom that's very common to see, I/Os taking a long time, and where the root cause is not necessarily the symptom. Okay? So when you're starting to do weight statistics analysis, as with any new system that you're going to be using, any new technology you're going to be using, there's a bit of a learning curve. And the weight statistics learning curve is very steep but very short. Right? The first couple of times that you're using it, you're not going to really know what you're looking at, but very quickly, once you start to understand some of the more common weight types, then you're going to be able to figure out an idea of what's going on in your system. So proficiency in using weight statistics, you're going to have to know, first of all, how to get the data back correctly. There's two DMVs that I'm going to show you, and as with most DMVs, if you just do a select star from the DMV, it's not going to give you really meaningful, useful, human, actionable information. You're going to have to do some kind of post-processing and so on of the data. So I'm going to show you how to do that. You also have to understand what some of the common weight types mean. As we're going to see as we go through the slides, there's probably 5 or 6 weight types that are going to crop up over and over and over again on most systems out there across the world. And as we go through those, you'll understand why that is. Now, coupled with understanding what these common weight types mean, you have to also take with a grain of salt everything that you read on the internet, or most things you read on the internet about those various weight types, because there's all kinds of inappropriate and horribly wrong advice about these various weight types. An example is if you see lots and lots of CX packet weights, then set your max DOP setting to 1. It's a horrible, horrible piece of advice. Okay, basically, that's a knee-jerk against that particular weight type showing up. And by setting max DOP to 1, you're turning off probably one of the best go faster options that SQL Server has, which is to be able to make use of parallel CPUs. You're also going to want to recognize a few of the patterns that exist, and a very common one is seeing CX packet weights along with what I call page I/O latch share weights, and I'll explain both of those as we go along. And that says we're reading lots of stuff from disk in parallel, and that's a pattern that usually says we're doing a parallel table scan, and that may or may not be a good thing based on the workload that you have architected. Okay? And then, of course, as with any new thing that you're trying, practice, practice, practice. The more you practice, the better you're going to be at this. But as I said, the learning curve for this is pretty short. So once you run weight statistics analysis on a few servers, then you're going to have a pretty good idea of what's going on. Okay? Now, rather than just walking up to a SQL server that has some kind of performance problem, what's even better is to have a set of snapshots of what's been happening with weight statistics. So maybe every half an hour, you run a query that captures, say, half an hour's worth of weight statistics, and you persist that into a table. And that means that you can analyze trends that occur. And if you're, as well as an architect, if you're a DBA, then and somebody says, you know, at 2:30 in the morning on Saturday we had this performance problem, any idea what's going on? If you have this saved snapshot of what's been going on with weight statistics over time, you can go back to that time period, have a look and see what was happening with a few hours before that event occurred, and maybe figure out, well, okay, we had a trend of more and more blocking occurring. So maybe we had a blocking issue at that time. Let's have a look and see if we can figure out any batch processes that were running at that time, for instance. Maybe there's a problem there, and so on and so on. You get the idea. Okay. So weights. There's a kind of chicken and egg problem talking about weight statistics, where I'm going to have to make reference to some of how the threading mechanism works in SQL Server without actually having told you how the threading mechanism works inside SQL Server. But I'm going to get to that in the next few minutes. So if some of the stuff that I'm talking about doesn't quite make sense, hold off on the questions until I've talked about the threading model, because that should hopefully explain it. So what a weight means is, the way that SQL Server works is it has threads, and they are the things that are executing SQL Server code. And the SQL Server code is running along, and a thread comes across a piece of code that needs a resource. Now, the resource could be, for instance, it needs to acquire a lock, for instance. And so if the thread calls into the lock manager to get that particular lock, and it finds that somebody else is holding a lock in a conflicting mode, it can't acquire that lock. So because the thread is the one that's actually running the SQL Server code, it can't progress. It can't go and just say, oh, I didn't get that lock, I'm just going to carry on running. It has to wait until it gets that lock. And so it actually gets suspended. It has to sit there and wait. So it gets off the CPU, and it sits there waiting until its resource is available. And then it can get back onto the CPU again, and I'll explain that process in a little bit more depth. The thing that's being waited for, the resource that's being waited for, and how long the thread has to wait for that particular resource is tracked by SQL Server. And that's very interesting to us, because if we see a certain class of resources start to become very prevalent for waits, or we start to see waits for a particular resource start to take a lot longer, that can give us a clue about problems that are occurring inside SQL Server. Okay? Some examples of resources. I already talked about locking. So a lock, that's going to be represented by the name of the wait type is going to be LCK_M_XX, and the XX means that can be a variety of different things. So this stands for lock, mode, whatever. So that could be a single X for exclusive, an S for share, an IX for intent exclusive, and so on and so on. The next one down, reading a page into the buffer pool from disk, that's going to be the page IO latch_XX, and the XX could be EX for exclusive, SH for share, UP for update, something like that. So this is waiting for a page to be read in from disk. And then we have the CX packet wait that I mentioned. And this is, and I'll explain in depth what a CX packet wait actually means. And this is where a thread is waiting for other threads as part of a parallel operation to finish running. Okay? A lot more depth to that, and we'll get there a little bit later on in the deck. And then this guy, a latch. So any multi-threaded concurrent system where there are data structures involved has to have some kind of mechanism for making sure that there is synchronization between the various threads for access to one of those data structures. And the way that that works inside SQL Server is by a mechanism called a latch. So for instance, a data structure that might hold the representation of files within a file group. Okay, it's called an FGCB, a file group control block. That's going to be protected by a latch, and the latch can be acquired in exclusive mode, in share mode, and so on. And this latch could be something that threads have to wait for. Okay? Now, I don't have time to talk about latches in any more depth in this talk, but if you go to the Pluralsight, if you get the Pluralsight code from me, or if you already have a Pluralsight subscription, there I have a 4.5-hour course on wait statistics that you can watch that talks about latches in an awful lot more depth. So before we get into thread scheduling, any questions on what I've talked about so far?
We have one question so far. It's about the TempDB, and it's basically asking if the TempDB is saturated, will adding more TempDB data files help?
It depends on your definition of saturated. If there's if the saturation is for I/O, then potentially, and it depends on how you're going to lay them out in your I/O subsystem. If the saturation is for multi-threaded access to, for instance, allocation pages that are already in memory, then probably yes as well. And we'll talk about that specific case a little bit later on in the deck. So let's hold on any more on that particular question until I've talked about that case later on in the deck. Okay.
That was the last question.
Okay. Thanks, Rob.
Oh, you're welcome.
Okay. So thread scheduling. SQL Server does its own thread scheduling. Okay. Now, Windows generally does thread scheduling, but SQL Server does its own because SQL Server is essentially a giant operating system in its own right. You know, it's a server class product, and it's really an operating system, but it has to run within the context of Windows. So it tells Windows that it's going to do its own thread scheduling, and this is because it's more efficient for SQL Server to do its own thread scheduling than to allow Windows to do it. Okay. Right down at the bottom, though, it says if a thread inside SQL Server has to call out to Windows for some reason, then the thread has to switch back to preemptive mode, where Windows controls what's going on with that thread, because that thread is essentially running Windows code at that point, where it's called outside of SQL Server. But in general, SQL Server does what's called non-preemptive scheduling, where it is managing its own thread scheduling. And we're going to talk about what thread scheduling is over the next few slides. So every processor core has a scheduler inside SQL Server. For example, the laptop I'm doing this presentation on has one CPU. It has 4 physical cores. I have hyperthreading enabled, which means I have 8 logical cores. Each one of those 8 logical cores has a scheduler inside SQL Server that can be used for running threads for queries that users submit to SQL Server. Okay. There are some other kind of background schedulers that we can ignore for the purposes of this, but every processor core, every logical processor core has a scheduler. Okay. You can look at what's going on in the various schedulers using this DMB, DMOS schedulers, and I've got a demo of doing that in the Pluralsight course. Okay. I don't have time to go through that one today. So this is what a scheduler, in effect, looks like, if you will. Okay, there's three parts to the scheduler. There's the processor, and only one thread at a time can be running on the processor. There's the waiter list, where all of the threads that are waiting for a resource are sitting. And then there's the runnable queue, which is all of the threads that have been waiting for a resource, have the resource now available, and are just waiting to get back onto the processor, waiting for their turn. Okay, and we're going to look at a couple of transitions in a bit more detail over the next few slides. Basically, your threads go round and round and round this loop in a clockwise fashion until it's finished processing your query. The various states that a thread can be in, there's three states that you can see, and you'll see these states in things like sysprocesses, sys.dmexec requests, something like that. And the states are as follows. Running, only one thread per processor, sorry, per scheduler can be in the running state. That's the one that's actually executing on the processor right now. All the threads that are waiting for a resource and don't have their resources yet are called suspended. And all the threads that have their resource and there's nothing else stopping them running apart from they're not the one running on the processor, they're called runnable. Okay, so threads transition from running to suspended to runnable back to running and round and round and round. So going from running to suspended, a thread is going to continue running on the processor until it comes across a piece of code that needs a resource and the resource is not available. So for instance, we have a thread from SPID60 that's running on the processor, and then it needs to read a page from disk. So what's happened is the thread has called into the buffer pool and said, I need a copy of this particular data file page in memory. The buffer pool has looked, or the thread has run buffer pool code that's looked to see if that particular page is in memory. The answer is no, and so a physical I/O is issued to get that page into memory. Our thread is now suspended. It gives up the CPU and it goes onto the waiter list. Now the waiter list is called a list because it's unordered. Okay? If it was ordered, it would be called a queue. Now it's unordered. That means that any thread can go into the waiter list at any time. Any thread can be removed from the waiter list at any time. There's no ordering. So just because our SPID60 thread was the last one that came into the waiter list doesn't mean it's going to be the last one to get removed from the waiter list. The time that a thread stays on the waiter list, stays being suspended, is entirely dependent on what else is going on the server, the resource that it's waiting for, right, and how long that particular resource takes to become available for that thread. So any thread at any time can be told that its resource is available and moved off the waiter list. So there's no boundary, there's no bounding to how long a thread can sit on the waiter list. It can sit there forever if necessary. And there's no limit to how many threads can actually be waiting on the waiter list on any particular scheduler. Okay. Now when a thread moves to the waiter list, its state becomes suspended, and the process of it moving from the processor to the waiter list is also called being suspended. Now there's a slight twist to this whole mechanism, which is, what if a thread is running on the processor and doesn't need a resource? So for instance, if a thread is involved in a table scan and there's nothing else running on the server and there's just one thread running and all the pages for that table are in memory, that means that you could imagine the case where the thread can keep running and running and running and running, processing a page, get the next page, processing a page, get the next page, and it never comes across a case where the resource that it needs is not available. Okay? It can't just keep running forever. Every thread must voluntarily give up the CPU after 4 milliseconds. That's called the thread's quantum. There's no way to change that. This is just how SQL Server works. So after 4 milliseconds, the thread is supposed to give up the processor. And it does that by, if it's in a piece of code where the SQL Server developers have realized, oh, this is a piece of code where a thread could just run and run and run. Every so often through that code, the SQL Server developers will have sprinkled calls out into the SQL OS system, the bit of SQL Server that runs scheduling, saying, how long have I been running? Have I been running more than 4 milliseconds? And if the answer comes back saying yes, then the thread itself moves itself off the processor. So there's no kind of Uber scheduling thread that controls what's going on a scheduler. The threads themselves are responsible for moving off of the processor to the waiter list or off of the processor if it's run for more than 4 milliseconds. Okay. If a thread gets into a piece of code and there's no call out saying, do I have to yield the processor, and it runs and runs and runs and runs, this is called a non-yielding scheduler. And 100% of non-yielding schedulers are SQL Server bugs. And the only way you can get out of a non-yielding scheduler is to bounce SQL Server, because there's also no way to kill that particular SPID, because the same piece of code that responds to kill signals is also the one that tells the thread that it's been running more than 4 milliseconds. So if the thread doesn't check, it's never going to get killed and never going to get off the processor. Now, in that special case where a thread yields the processor, it doesn't go to the waiter list because it's not waiting for anything. Right? It goes directly to the bottom of the runnable queue because it's immediately able to carry on running. However, it must register a particular wait type, and the wait type that it registers is SOS scheduler yield. Okay? Going from suspended to runnable. If we have a thread that is on the waiter list and it is told that its resource is available, then it gets moved to the runnable queue. Now, it's very interesting there. I said if it's told that its resource is available. The thread is sitting on the waiter list. It's not running any code. It can't run any code because it's not on the processor. So it can't go and poll every so often saying, hey, do I have the resource? Do I have the resource? Do I have the resource? It has to be told by another thread that its resource is available. And that is called being signaled. So when a thread is signaled, for instance, our SPID60 there, it's told your page is now in memory. So you're now runnable. You can go to the bottom of the runnable queue. So what in effect happens is a thread notices that the I/O that our thread issued has completed. And that I/O will have what's called an I/O completion routine that has to run. This other thread will run the I/O completion routine, and as part of running the I/O completion routine, it will move our thread onto the runnable queue on that scheduler. Okay. And the final transition is going from runnable to running. So if a thread is sitting there on the runnable queue and it slowly moves its way up to the top of the runnable queue, the next time the processor becomes available, it is the thread that's going to move up to running on the processor, and its state becomes running. So the threads transition around from running to generally to suspended, to runnable, and back to running. Every so often you'll have a thread that exhausts its 4 milliseconds quantum, and it goes from running directly to runnable. So any questions so far about those transitions?
Okay, we have a couple questions. I'll read a few here. Let's see. Threads. They're asking about threads. So threads limited to the number of CPUs available to SQL Server. Do the threads in the runnable... Oh, I'm sorry. That's two questions. So they're asking about the number of threads per CPU for SQL Server.
Okay, no, the number of threads is determined. It's actually it's worked out, and you can also alter it, although you generally shouldn't, with a startup parameter. I think it's -g that will change the number of worker threads you have. SQL Server, simplifying things, basically has a pool of worker threads that when a query needs to run, a worker thread will get pulled out of that pool of available worker threads and put into one of the schedulers, and it runs your query. Or if it's a parallel operation, it'll pull multiple threads out of the pool of workers, and it'll start running your operation. If you find that this pool of worker threads is exhausted, then you might see what are called thread pool waits. Okay, where you might have, and a cause of that could be, this is not something I was going to talk about, a cause of that could be you might have lots of connections all running parallel queries. And so, you know, if you have, say, 512 worker threads available, you have 100 connections on a DOP8 system, each using, say, 17 threads, then very quickly you're going to run out of threads available to these various queries. Okay, so the number of threads is not set at the number of schedulers. It's a number, it's quite a high number, and those threads are then used as necessary to run queries. When the threads are no longer required, they're taken off the scheduler and they're put back into the pool of available worker threads. All right, Rob, next question.
Okay, and this is kind of going back to that question a little bit. How many threads can be in the processor?
Only one thread can be running on a processor. The number of threads that are assigned to a particular scheduler doesn't have an upper limit. So, for instance, you could have, maybe you've messed around with CPU affinity masks, and so there's only one actual processor that's available for SQL Server to use. So there's only one scheduler, you might have, say, 100 threads running on that scheduler. Okay, it just depends on what the workload is. Or you might have an 80-core system with hyperthreading turned on, so there's 160 logical schedulers, and if you don't have very much going on, you might have a bunch of schedulers with no user threads running on them whatsoever. So it entirely depends on what the workload is, how many threads there are going to be per scheduler, but only one thread per scheduler can actually be using the processor at any one time.
Okay. Is there a limit to the threads in the runnable queue?
There is no limit to the number of threads in the runnable queue, just as there's no limit to the number of threads in the waiter list. However, if you see, if the number of threads in the runnable queue starts to get really large, like tens, okay, so like 20, 30, 40, something like that, what you might see is the length of time that a thread sits on the runnable queue starts to increase, obviously. Okay? And we haven't quite talked about what that time is called. It's called the signal wait time. So your signal wait time might increase. And if you find that the runnable queue on a lot of your processors is very large, that's a sign that you've got your CPU bounded. You've got CPU pressure. And so what you might want to do, what you might have to do is A, reduce your workload, B, split your workload over multiple machines, or C, if you're on an Intel architecture, you might consider turning on hyperthreading if you don't already have hyperthreading enabled, because that essentially doubles the number of schedulers. It's not going to double your performance, but it's going to alleviate some of that CPU pressure that you might be having.
Do you want to take one more?
Sure.
Okay. Let's see. Does the thread stay in the same scheduler for its whole life cycle?
A thread that's part of a query is going to stay on the scheduler it's been assigned to when that query started until that query ends. Then it goes back to the pool of threads, the pool of worker threads, and then it might get put onto a different scheduler. But once it's been assigned to a particular scheduler, it's not going to migrate to a different one. Okay?
Okay.
All right, carrying. Okay, so the various wait times, now that we've looked at thread scheduling, the time going from running on the processor all the way around the loop to going back on the processor again is called the overall wait time. Okay? So there's two components to that. There's the time that it's waiting for the resource to become available. This is known as the resource wait time, basically the time spent on the waiter list. And then there's the time waiting to get back on the processor after the resource is available, and that's called the signal wait time. So your overall wait time is resource wait time plus signal wait time. And to graphically illustrate that, imagine that we have a thread sitting there on the processor. It comes across a resource that it can't get, so it gets suspended. It goes onto the waiter list. It stays on the waiter list for a certain amount of time, okay, until it's told that its resource is available, and then it becomes runnable again. All the time in red is known as the resource wait time. The time that it spends sitting on the runnable queue waiting to get its turn on the CPU and then getting onto the CPU is called the signal wait time. Okay, all the time there in yellow. And the overall wait time is the resource wait time plus the signal wait time. Okay. We're generally interested in the resource wait time because the signal wait time is generally extremely small, either 0 or less than 1/10 of a millisecond, or maybe 1 or 2/10 of a millisecond. Now, in that question that I just answered about how many threads there can be on a runnable queue, if you've got CPU pressure, then you might see your signal wait time start to increase more than 1 or 2/10 of a millisecond. Okay, and that's a sign that you might have CPU pressure. So the two DMVs that you can use to look at what's going on with wait statistics. The first one is called DMOS waiting tasks, and I think of this as the what's happening right now DMV, because this shows you all the threads that are waiting for something right now. And if I'm going up to a slow SQL server, this is generally the very first thing that I'm going to look at. And I've got scripts that I'll show you that will show you how you can call this DMV, and the other one that I'm going to show you as well. Okay. It shows a whole bunch of information. Rather than just reading through the list of stuff on the slide, I'll wait until we do the demo in a few more slides and show you what this DMV does. So this one is the what's happening right now. There's another one which is the what has happened in the past, and this is the DMOS wait stats DMV. Okay, so this gives you an aggregate view of all the waits that have occurred since your SQL Server was started, or since you manually flushed out your wait statistics, because you can manually set the aggregate wait statistics to 0. Okay, and that can be useful if you're doing some kind of performance tuning exercise, or if you're wanting to do a demo of what's happening with wait statistics. Okay. And again, I'll show you what's going on with that DMB when we do a demo. But with both of these DMBs, you'll see when I do the demo that I don't just do select star from DMB name. Okay, there is a bunch of processing that I'm going to have to do to make the results useful to me. Now, when you're looking at the weight statistics that occur on a server, there's a couple of things that you have to bear in mind. You have to make sure that you're looking at relevant information. Okay? There's two facets to that. The first facet is there are a bunch of weight types that occur all the time. Okay? These are generally benign weight types which you don't mean that there's a performance problem, but if you leave them in the output of your weight statistics information, they're going to essentially pollute the output and maybe show up as the most prevalent weight type. An example there is lazy writer sleep. So the lazy writer is a background process that runs as part of the buffer pool. And whenever the lazy writer goes to sleep, it's incurring a weight, waiting to be woken up again. The aggregate time for the lazy writer sleep could end up being the most prominent of the various weights that are occurring on your server. And so it's better to just filter those out. And you'll see what I mean when I show you the code. Okay? So making sure that you don't have these kind of background weight types masking what's going on with the interesting weight types. And the second facet to making sure you're looking at relevant information is it's not just the weight type that we're interested in, it's also how many weights occurred for that weight type and what's the average length of time that a thread had to wait for that resource to become available. For instance, if you're analyzing weights say overnight, so over a period of 8 hours or so, and we saw that there were 10 million lock weights occurred. And out of those 10 million lock weights, 1,000 of the weights were for share locks. Okay? If the aggregate time for all 1,000 of those weights together was 50 seconds, then I'm probably not going to care, okay? Because that means that each one of those weights is, what, 5/100ths of a second. Now, if every single one of those 1,000 weights for a share lock was for 50 seconds each individually, then I would care, because that's a symptom of potentially a major blocking problem. Now, as an architect, you might know that you expect there to be some blocking going on based on what your code is doing, the isolation level that you've chosen. For instance, you might be running something in serializable isolation level for some reason, in which case share locks are going to be held until the end of a transaction. Okay? So that, again, may or may not be relevant to you with your knowledge of what's happening in the system. And as an architect, one of the things that you might be able to do is help developers and DBAs figure out what's a relevant weight type. Okay? What kind of symptom would you expect to see if the system is performing as you designed it to do, and what might be a symptom that you don't expect to see. So here's the results of a survey that I did last year. And I did a similar survey about 5 years ago, and the results of the two surveys 5 years apart were interestingly different. And the major difference between the surveys was this guy, OLADB weight. Now the OLADB weight 5 years ago was somewhere down here, like number 5 or 6. And now, last year, and if I reran the survey again today, this would also be the number 2 weight type. Okay, so that was an interesting change of behavior that I'll explain in a second. So what the survey was I put out some code on my blog and said, if you run this code, it's going to capture a 24-hour snapshot of your weights, send them to me so that I can produce this survey. And also, if you send them to me, I will tell you what each of the weights in your snapshot actually means. And it was a really stupid thing to do because I had 560 people send me their weights, and it took me about 3 months to work through all of the email replies explaining what everybody's weight types meant. But I did get all this cool information. So if any of you out there listening to this were one of the people that sent me some information, then I thank you for that. So this is a distribution of weight types that I would expect to see if I walked up to a random SQL server somewhere in the world. I'd expect to see something like this. Okay? So what we're seeing here is the very top weight type is CX packet, and this means parallelism is happening. Okay? The OLADB weight type, and we're going to talk about this one, this one, this one, this one, this one, okay, as part of the rest of the deck. So the OLADB weight type is somebody using the OLADB communication mechanism under the covers. Okay? This is waiting for a write to happen to the transaction log. We're waiting for an application to respond to SQL Server. We're waiting for a page to be read in from disk. Okay, so these three I'm not going to talk about in more depth. So this one is we're writing, this is a backup process that's writing out to a backup file. And it's common to see backup I/O weights if you're backing up to a tape drive or you're backing up to a network share, for instance. Now, in concert with backup I/O weights, you often see backup buffer weights. So if your backup process is using multiple threads, then there can be contention amongst the multiple threads for access to a buffer to write information into, to then write out to the backup file. So these two together are backup weights. And then this guy we mentioned, this is where a thread is able to run for 4 milliseconds and voluntarily gives up the CPU. Okay. A lot more information about this one I've got on my blog. Now, the interesting thing, as I mentioned, was about OLEDB weights and how they bubbled up to be the number 2 weight on most servers across the world over the last few years. Now, the common knee-jerk reaction to seeing OLEDB weights is, oh, it must be a linked server problem, because linked servers use OLEDB. Okay. Now, I don't think, in fact I know this to be the case, that there hasn't been an explosion in the use of linked servers over the last 5 years. However, what there has been an explosion in the use of is the use of third-party performance monitoring tools. Now, if you install one of these third-party performance monitoring tools, very often what they're doing under the covers is running DMVs, okay, to see what's going on your server. And most of the DMVs are written as OLEDB rosette providers. Okay? They're going to be something like SelectStar from Open Rosette, the name of the DMV, under the covers. And so you've got lots and lots and lots of DMVs being run over and over and over on your server and incurring OLEDB weights. So if you go to your SQL server and you look at the weight statistics and you see hundreds of millions or billions of OLEDB weights, each for something like 1 or 2 tenths of a millisecond, you've got a third-party monitoring tool that's sitting there running DMVs over and over and over and over. That's not a problem, but it's going to generate lots of OLEDB weights. So you have to understand what those are so that you don't get freaked out when you see all these OLEDB weights. Okay. And if you're interested in the survey, then you can go to this link down here. I've got a little bit.ly link for you, and that goes across to my blog. And for every single one of the weight types that are in that list, I explain what they mean. Okay. So how are we doing? Any more questions so far?
Yeah, we do. Basically, cover up a little housekeeping really quick. Yes, we will have the recording on the past site. And one person asked, do you share out the chapter deck, the chapter slides? Is that on your website?
Yeah, no, Rob, what I'll do is I'll create a PDF of the slides and I'll send that to you as well as a zip file of the demo scripts.
Okay, thank you. Here's a question about asynchronous network I/O, and basically they're getting an asynchronous network I/O greater than 6,000, and they're just going to say, what does this mean?
Okay, so for questions about all of these weight types that I'm scrolling my mouse across now, wait till after I've had the slide that explains what they are. Okay, and if you still have the question, then I'll be happy to answer them for you.
Okay. Another question was, what is a resource semaphore weight?
Okay. So this is one that I'm not going to talk about. I wasn't going to talk about. A resource semaphore weight is where so the way queries work is they get compiled and then put into the plan cache, and then at some later point, possibly immediately, they are then executed. So the query execution portion of the query processor does a number of different things before it starts running a query. 2 of those things are it decides if the plan is parallelizable, how far to parallelize the plan. The second thing is it gives the query what's called a query execution memory grant. It gives the query some amount of memory to be able to run in. And so that's the memory that it can use to do aggregations and sorts and spools and things like that. Now, if the query needs a certain amount of memory and that amount of memory isn't available inside SQL Server for the query to run, then the query is going to not be able to run, and the thread that wants to start running the query is going to wait for a resource semaphore. So it's basically a sign that you've got memory exhaustion problems. That doesn't mean you need to add more memory, potentially. That could mean that you've got a lot of queries that are doing a lot of stuff in parallel, for instance, or maybe they've got sorts in their query plan, just as a very simple example, and you might want to go and figure out why that particular query needs so much memory. And there's a DMV that you can use, sys.dm exec, I believe it's query execution memory grants. So you can see a list of all the pending there's another one called pending execution memory grants. I can't remember the name off the top of my head, but you'll be able to find them on Google, and if you can't find them, shoot me an email. So there's one that says memory grants that have happened, and another one that says memory grants that are pending. So you can see what's in the list of pending memory grants, and you'll be able to see what the query plan is by joining up with some other DMVs to see what the query plan is that's waiting for a particular memory grant to become available. Now, just because a query is waiting for a particular memory grant doesn't mean it's never going to run. It might be given a reduced memory grant and run, for instance, in that. There's another related wait type called a resource semaphore query compile. And that means that a certain amount of memory is required by the query optimizer to even compile the query. And the memory pressure on the system is so much that it can't even get the memory required to compile a query. Not anywhere near as common to see as resource semaphore. And in fact, resource semaphore waits are not common to see, but resource semaphore query compile is a magnitude less common even than resource semaphore. Right?
Okay. I'll give you one more here.
Sure.
They're basically running SB Who2, and they're getting a status of sleeping, and they just wanted to get some information. What does that mean?
If I remember rightly from what SP Who is doing, sleeping, that is a connection that's not actually doing anything at the moment, and the connection is still active as far as SQL Server is concerned. So imagine you've got a window in Management Studio that is connected to SQL Server, but you're not actually doing anything with it. That's going to show up as sleeping.
Okay.
Okay. All right. Carry on.
Thank you.
So getting into some of the wait types and what they mean in a bit more depth, and I'm about 3 slides away from doing a demo now. So the page I/O latch wait, I mentioned this earlier on. This is waiting for a page to be read into disk, read in from disk. It doesn't mean that there's an I/O subsystem problem. Okay, it could be that the I/O subsystem is overloaded if you're seeing that the time that the page I/O latch wait is for is more than you would expect the I/O latency for your I/O subsystem to be. So for instance, if you're running on an SSD, you might expect your I/O latency to be maybe 1, 2, 3 milliseconds. If you're running on 15K SCSI drives with a fast enough network, you might expect to see maybe 4, 5, 6, 7 milliseconds, something like that. Okay? If the average time for the page I/O latch wait is higher than that, okay, then you're overloading your I/O subsystem in general. Okay. So what would I do? If I wanted to figure out what's going on, as we're going to see when we see some of the wait types, the DMOS waiting task DMV gives you a resource. Okay, what is it? What is the resource that the thread is waiting for? And for a resource involving data file pages, it will actually tell you the data file page itself. So it's going to tell you the database ID, the file ID, and the page ID, and you can figure out what those are. If you go over to my blog here, this is my wait statistics blog post category. If you go down here, I've got a blog post called Finding a Table Name from a Page ID. And you can use the method that's in there to take a page ID from the output from DMOS waiting tasks and figure out what table it's from. Okay, so if you've got a query plan that's involved that you're seeing page I/O latch waits for, okay, and you might click on the query plan and see that there's 10 tables involved. Okay, which table is it that I'm getting the reads on? Okay, then you can actually figure out exactly what table that is from following what's in that blog post. Okay, you could also have a look at what SQL Server is seeing as far as the I/O statistics are in terms of the I/O latencies, read and write, for particular files using the DMV DMIO virtual file stats. And again, in that blog post category, I've got a script that's going to allow you to capture the I/O latencies for all the files on your server in a period of, say, 30 minutes. Okay. You might also look for patterns. For instance, page I/O latch waits combined with CX packet waits often is a sign of parallel table scans. And so I'd want to know, what table is this on? Do I expect there to be a table scan happening for this particular query? Am I got missing non-clustered index, for instance? Do I have statistics that are out of date that are forcing me to do a table scan rather than an index seek? Do I have some code that's been badly written? Right? And so the code is operating on every data value in a column, for instance, an implicit conversion, classic case where you might be comparing dates. And so you have a date function that's operating on the column in the table rather than operating on the parameter that you passed into your stored proc, for instance. That's going to cause an implicit conversion where it has to do a table scan because it can't use an index. So all kinds of things that you could look for seeing whether you should be doing a table scan, for instance. And then you might want to look just in general and see, do you have, are you under memory pressure for your buffer pool? Is the page life expectancy lower than your normal? Okay, so you have to have some kind of performance baseline to be able to figure out whether you've got any kind of memory pressure happening. So you can compare what your memory pressure is now, or your memory statistics are now versus what they were when your system was running when you took your performance baseline. Okay. It could just be that you've hit a tipping point and your data volume is growing over time, and you've just hit a tipping point where the amount of data necessary to process your workload cannot fit in memory anymore. And so you're having to do more and more reads, which is slowing down what's going on the server. Okay. Now, look at the name of this wait type, page latch, and we go back up, page IO latch. These are often confused, okay? And people often get this guy, page latch, confused with page IO latch. There is no IO in the name here. There is nothing to do with the IO subsystem for this particular wait type. Okay? So the mistake that people make here is, oh, they see page latch waits and they go and add more memory, or they go and add more data files or something like that. That's not going to help. Okay? There is one specific niche case where adding extra data files can help with page latch waits, and that's around TempDB. Okay? But it's got nothing to do with I/O. This wait type has got nothing to do with I/O at all. What this is we have a data file that's already in memory, and there are multiple threads trying to get access to the data file page that's already in memory, and we have multiple threads trying to get access to this particular page. Right? If all the threads need to acquire access to this page in exclusive mode, obviously only one thread can be doing that at a time, and so that becomes a bottleneck. Right? So a very common bottleneck is the one that a question mentioned earlier on, which is, what if you have some kind of problem with TempDB? If you see that the resource for the page latch waits is in TempDB, so database ID 2, and are certain page IDs, for instance, data file ID 1, page 1, or page 3, then these are allocation bitmaps. And the likely workload you've got is a large number of concurrent threads creating and dropping small temp tables. Okay? And the creation and deletion of temp tables means we're allocating and deallocating individual pages that have to be changed in allocation bitmaps, and so those become a contention point. Now, one of the ways to work around that, if you can't change your workload, can be to add more data files, because that means that the allocation load of those temp tables is spread across the multiple data files, thus reducing the contention on the allocation bitmaps. That's nothing to do with I/O. Okay, so you're not affecting any I/O there. You're just spreading out the contention over multiple data files. Okay. Another case of page latch contention could be what I call an insert hotspot, where you might have and I'll show you an example of this in a second. You might have a table that has an int or a big int identity key for the clustered index and a small row width, maybe say 100 bytes. So you can get 80 records per page. If you have lots of concurrent inserters, then they're going to be generating cluster key values from the identity column that are all going to go on the same page. Only one thread at a time can be modifying that page. And so you have contention for a page at the leaf level of a clustered index because of the way that you've designed your table. Okay? What's the workaround from that? Use a more random key. You might decide to change it to, for instance, a random GUID column as your clustered index key, which a lot of people think is complete anathema. You should never do that. No, that's not true. It depends on what your design is and what the performance issues that you've got from your design. The only way to work around an insert hotspot is to split the inserts over multiple points in your table. You could do that by using a GUID column, taking into account the fact that a GUID cluster key is going to start to cause fragmentation, mitigating that using a fill factor, or you could use partitioning. You could use a kind of fake partitioning scheme that's going to split the inserts over multiple partitions or something like that. But all of these are basically saying we have contention at the page level in memory rather than contention for reading a page into memory. Very important distinction. And then locking weights. So I already mentioned locking weights a little bit. Basically, a thread wants to get a lock on a resource in a certain mode, and another thread is already holding a lock on the same resource in a conflicting mode. For instance, we want to insert something into a table. So we need to get a table intent exclusive lock to be able to do that. However, another thread has inserted lots and lots of rows and has escalated to a table exclusive lock. Nobody else can get any other locks at all on that particular table. That's one of the causes of blocking problems, is lock escalation. Okay? So you might have to redesign your access strategy. You might have to add multiple non-clustered indexes. You could end up using snapshot isolation to help prevent blocking problems. Okay? One of the things that you can do to figure out what's going on is what's at the head of the blocking chain. So our thread is blocked by something else. Is that thread blocked by something else as well? And follow that list of, or a set of links to find out what's at the head of the blocking chain. Okay? And following that blocking chain might show a non-locking issue. For instance, okay, just because you see locking problems doesn't mean that locking is the issue. Consider transactions. A transaction that modifies some data in a database has to hold its locks, or its exclusive locks at least, under the read-committed isolation level until the transaction completes. Right? What if the transaction takes longer and longer to complete? That means those locks are going to be held for longer and longer, and other threads are likely to be blocked. So what could cause a transaction to take longer to complete? For instance, somebody could have just implemented a synchronous availability group replica. And what that means is when a transaction goes to commit, the final log block containing the commit log record for that transaction has to be sent across to the synchronous replica and written out to that replica's log drive. If the time that takes starts to increase, maybe from a network issue or from an I/O subsystem issue over on the replica system, then that translates into extra time it takes for our transaction to have to wait before it can release its locks. And so a locking problem could end up being something to do with a synchronous mirror or a synchronous availability group, for instance, not necessarily a pure locking issue. Another thing I like to advise people to do, obviously, we don't have time to go into an hour's worth of how to debug locking, right? But you could go and look at a guy called Michael Swart. I believe he's an MVP, and he has a bunch of good blog posts around locking and blocking and how to investigate them. And he has a particularly good one about a thing called the blocked process report and how to use that, where if you have blocking going on for a number of seconds, for instance, you can configure SQL Server to automatically create a report on the various queries that are waiting for those locks and what the query was that was blocking everything else. Okay? He also has a nice flowchart for how to investigate locking issues as well. Now, if you're going to take me up on the offer of getting free access to Pluralsight, there's a course that Jonathan Cahias, who works for us, has recorded on analyzing and preventing deadlocks. Right? And that also has some information about locking and blocking issues as well. So I'm going to go ahead and do a demo now, where I'm going to pull a bunch of this stuff together and show you these two DMVs, and then we'll see if there's any questions after that. So again, I'm going to give a zip file of all of these demo scripts to Rob, and he'll be able to put that up on the PASS website for you. So first of all, before we create our scenario, I'll show you the scripts I'm going to be using. The first one is looking at DMOS waiting tasks, the what's happening right now DMV. And as you can see, I'm not just calling DMOS waiting tasks. I'm joining up with a whole bunch of other DMVs. That's so that I can give you, or the script can give you things like who's running this, where's it coming from, what program it's running from, what was the last SQL text that was used, what was the graphical query plan or a link to the graphical query plan that's in operation. I'm filtering out everything that's a system process by just looking at user processes. And if I go ahead and run this right now, it's going to give me back nothing because there's nothing actually running on my server. But once I start a scenario, you'll be able to see some stuff actually happening. Now the other script is using DMOS wait stats. And you can see from this, it's not just doing a select star from DMOS wait stats. I'll explain this script in a second. If I just go ahead and do a select star from DMOS wait stats, then it's going to give me one row for each wait type there is, and this is on 2014, so there's 771 different wait types. And you can see that the raw information given out is not very human readable. I can't easily see where there are weight types, and there's a bunch there. I'm going to have to scroll down to find all the different ones that have non-zero weight types. And I don't have the per weight type times. Okay, what I have to do is, in fact, it doesn't even give me the resource wait time. It only gives me the total aggregate wait time, the total aggregate signal wait time. Okay, so to find out the average resource wait time, which is what we're really interested in, we're going to have to take wait time minus signal wait time and then divide by the number of times that this wait has been waited for. Now, because this information is an aggregate since the server started in general, you might find that if you have a spike in activity over a certain wait type, that it's essentially masked because the number of waiting tasks and the aggregates mean you're just getting an average. This is why it's really useful to have some code running that does a snapshot every half an hour of what's happened over the last half an hour, rather than just having, say, this might have been everything that's happened over the last 3 months since my SQL Server was restarted. Okay. Now, if you want to look in a better fashion, what you're going to do is run code like this. So what this is doing is it's taking all the waits that have occurred and it's ordering them and giving them to me in terms of descending order of the most prevalent wait types based on the overall wait time, the aggregate wait time for each wait type. And it's going to give them as a percentage of all the waits that have occurred, and it's going to give me the top 95% of waits. If I just run it, you'll see what I mean. Okay, so since I restarted my SQL Server earlier on this morning, these are all the various different waits that have occurred. And you can see how it works. So this is what we're given via the DMV. These are the raw things. I've worked out this, and then I'm giving the averages. So these are in seconds. So for instance, this guy is 3.7 milliseconds. And we can see the percentage of all the waits that have occurred. And generally, when you're looking at wait statistics, you're just looking at the top 3 or 4 wait types. You don't have to get down into the weeds of looking at these little tiny guys down here. We don't generally care about these. Okay. So very quickly, what are these? This is Sherlock's. It's running crash recovery on, let me see, so this isn't, the FFT stands for Fast Fourier Transform, and it's part of crash recovery. I can't remember exactly what that part is. This is waiting for pages to be read in from disk, doing some kind of security operation, waiting for pages to be read in from disk. So this is for exclusive mode, this is for share mode. Schema modification lock, waiting for extended store procedure to run, write stuff out to disk. This is likely to be zeroing out the tail end of the transaction log during crash recovery. More zeroing out of transaction log, waiting for an application to respond, and a kind of catch-all for stuff to do with doing operations on files out in the OS. Okay. Now, all these wait types, they mean something, and there isn't a huge amount of information out there on what all the different wait types mean. There is a white paper that was published in 2006 that talks about some of the wait types, but it's kind of old now, and it doesn't have all the hundreds of wait types that were added after 2005 came out. So there isn't a resource out there on the internet that has all the different wait types yet. I am working on a website as part of SQL Skills that's going to have every single wait type and latch class that has occurred since SQL Server 2005 with what they mean, what you should know about them, and how to go about doing more analysis, and where they occur inside SQL Server. And that'll probably be available. It's an awful lot of work. It'll be available sometime March or April, and I'll announce that on my blog. Okay, so if you're interested in doing a lot of kind of spelunking around with what's happening with wait types, then look out for that resource coming out. Okay. Now, two things that I've got. I've got 2 copies of this wait stats script, so that I can, in the demo, do something, show the wait stats, and then clear out the wait stats, like so, okay, and then do something else in the demo and do a comparison between the two. So let's actually do something. So what I've got here is I'm going to create a scenario, and there's 3 different scenarios that I'm going to play with, and each of them have an instructions.txt. And what I'm going to do is I'm going to fire up, I'm going to create the scenario, I'm going to fire up a couple of hundred clients all running my code. And it's very simple code. We're going to create a table for this one, and we're going to have 200 clients inserting into the table. And the way that I do this so that you guys can go and play with this yourselves is I don't want to use any third-party tools, because then you have to go and buy it or download it. I just got this guy, add 200 clients.cmd, calls run client 200 times, which just does a SQL CMD and calls hotspot-client.sql. So that's how I'm running my code, and it's going to be very simple for you guys to do as well. Okay, so the first thing that we're going to do is we're going to go ahead and create our database. And then we're going to create a very simple table, and this is an insert hotspot that I'm creating. I've got a table with a very small clustered index row, and I'm going to have 200 threads inserting into that, and we're going to cause basically an insert hotspot to appear. Let's go ahead and create this, and then we'll start up our 200 concurrent connections. Like so. We go back up to Management Studio now. Let's have a look and see what's going on. So I just hit F5. Now I'm seeing a whole bunch of threads, in fact 196 threads, okay, waiting for page latch. So these are not IOs that are happening. These are waiting for access to a page that's already in memory. Okay? And if we look across, we can see the resource description. Database ID 5, file number 1, page 805. So if you wanted to see exactly what table that was, you would take this resource description, go across to that blog post that I showed you earlier on, and follow the instructions, and it will tell you which table this is part of. Okay. So the script shows you the SPID. It also shows you which thread within the SPID. Okay. So if there's parallelism happening, you're going to see non-zero exact context IDs. Okay. So 0 just means this is either not a parallel operation, or it's the control thread for a parallel operation. Okay, so these aren't parallel operations. Which of my 8 schedulers this thread is running on, how long it's been waiting in milliseconds. If this was locking, it would show us this. We'll see an example of that in a second. If it was a CX packet wait, it would tell us which node in our query plan, and I'll show you an example of that when we do that demo. The program name, the SQL text that's being run, which database it's in, the graphical query plan. So if I click on this, it's going to show me the graphical query plan for what the thread is actually part of. Now this is obviously a very simple one, okay, so these are all contrived examples, but in a more complex situation, you might have 10 tables involved, which is why taking that page ID, you can then reverse engineer and see which of the tables in your query plan the reads are on, and then look at that particular portion of the query plan and figure out what's it doing, why is it doing a read. Okay. So if I go across and look at wait statistics, and just run this again. Now we're seeing that all that stuff I showed you before, that's all been masked because the waits that are occurring are way more prevalent and relevant to us than the little waits that are occurred while I booted up my server. So we can see that now we've got 62% of the waits that are occurring are for page latch. Now, the two ways of approaching wait statistics are coming in at it from the waiting tasks point of view, and coming at it directly from the aggregate point of view. If I came at it from the waiting task point of view, I would see immediately I have a hotspot. Okay, because as you can see scrolling down, all of these are basically for the same page ID. So I've got a hotspot for sure there. Right? I want to figure that one out. If I came at it from the wait stats point of view, this doesn't scream hotspot at me. I can't tell from just this aggregate information whether I've got a hotspot or not. If I run F5 again and we look at the wait count, so we can see it's going up really quickly. Okay? So that would make me say go over to waiting tasks to see what all these page latches are for. But just seeing this information, one snapshot of this doesn't say that there's a particularly an issue. Okay? Now, if I just saw this, I would say, well, okay, I've got page latch going on, lots of them. I don't know how long the server's been up, so I can't tell whether that's an issue or not. Each one's like 4 milliseconds, so I mean that's a reasonable amount of time that each thread is waiting for. But again, I can't tell whether these waits are over the course of a week or over like 5 minutes, as it is in our contrived case. Okay, we've got some logging waits going on. Again, we've got a lot of them, but that could just be normal because the log often shows up as a wait statistics. 2.3 milliseconds for a log write. That doesn't seem out of the ordinary given that I've got a log on, my log is on an SSD. Okay? So I can't tell just from looking at this whether I've got a performance problem. Okay? So multiple snapshots would be used, or going across to waiting tasks. Okay. So that's just looking at those DMVs. If I change my wait statistics now, change my demo, I'm going to change my clustered index so it doesn't allow row locks anymore. So now everything that wants to insert has to take a page exclusive lock. I'll go ahead and run that. Right. And if I go ahead and hit F5 here, now I'm seeing all the threads are waiting for locks. They're waiting for exclusive locks. Now, if we look at the resources are one of a couple of different pages. So again, this is a classic hotspot. Now, if I go across to wait stats, let's see. Now, this is still showing a bunch of the stuff that happened before. If I empty out my wait stats, so I'm just showing you what's happening from this new demo. If I give it a few seconds and then hit F5, now I can see that basically everything that's happening now is exclusive lock waits. If I walked up to a server and looked at wait stats and saw this, I would see that there was a problem. Okay, because basically 100% of everything that's going on is lock waits. Now, 38.5 milliseconds by itself doesn't say there's a problem, but the fact that almost 100% of all the waits are exclusive locks says that there's an issue to me. So I would go back to waiting tasks, I'd run that, I'd see, oh my goodness, it is all locking waits. If there wasn't a specific pattern, right? For instance, if this was lots of different page IDs, then I might have to go and look at the query plan and figure out what's going on. If this was table lock or tab lock, then I could say, well, maybe there's a lock escalation thing has happened. So I might go and look at the blocking session ID. So this says blocking session ID 58. So let's go and look for session ID 58. So session ID 58 is blocked by 95. So I go and have a look at 95. And so on and so on and so on until I found the head of the blocking chain. And then I could go across and see, okay, the head of the blocking chain, have a look at its plan. What is it doing? Or what is it waiting for? And again, more information on dealing with locking and blocking problems in those blog posts by Michael Swart. Great. So there's a couple of very contrived examples, obviously, to show you using those two scripts and some of the things that you might see. So any questions on what I did in that demo, or any other questions so far, Rob?
Yeah, we have a few.
Okay.
Let me scroll up here. One of the questions kind of had a lot of white space, so here's one. How do I deal with locks when rebuilding indexes in replicated tables?
So is the question that you're rebuilding the indexes on the subscriber, or you're rebuilding the indexes on the publisher, or are you wanting to replicate the rebuild of the index itself? Okay. So I'm going to guess that. Well, let me see. So on a publisher, would it actually make on a publisher it wouldn't make any difference because
he just wrote back publisher.
Oh, so on a so what is the problem that you're seeing?
Let's see if he writes back.
Because there shouldn't be any issue with replication, because replication looks at it harvests committed transactions from the transaction log. Replication doesn't get blocked by locks occurring on tables. Now it could be that you've got other transactions that get blocked occurring on tables while an index is being rebuilt, but that's not going to have anything to do with replication unless your problem is you're wanting particular changes to go through and get propagated to your replication subscribers quickly. But again, that's not a replication issue. That's just a general index rebuild issue. Now, if you wanted to work around index rebuild locking, you could use online index operations in Enterprise Edition, although there are still a couple of points where you might have blocking. There's a table share lock that occurs at the start of the online index operation, and then there's a table schema modification lock that occurs at the end of the online operation. But for the length of time that the online index operation is running, it's a table IS lock, which shouldn't really block anything. And then in 2014, there's a new thing you can do where if you've got either online or offline index rebuilds happening and they're wanting to take a table lock, then you can tell the system that I want that particular table lock to essentially wait and not to block everything else. And if it can't be held after a certain amount of time, to just die and not do the online index operation. And I can't remember the syntax to do that, but you can search for that. So maybe that's the question that the person is interested in.
Yeah, he just went on a little bit and said it's a big. He's waiting on, and he's running standard edition.
Okay.
So
in that case, on 2014, you might be able to use that kind of delayed locking, or on earlier versions you can't. And then what you're going to want to do is, instead of using an index rebuild, you want to use an index reorganize, or if you're on a really early version, you might use DVCC index defrag. Both of those, DVCC index defrag was the early version that I wrote for 2000, SQL 2000, and alter index reorganize was the 2005 replacement for it. And what both of those do is they only require table intent exclusive locks. So other things can be inserting and reading from the table at the same time as you're reorganizing your index. So that's what you're going to check out, is using alter index reorganize rather than alter index rebuild in that case.
Okay. Here's a question I find pretty interesting myself. They have a tempdb file, and they added an additional file to the tempdb, and with not the NDF extension, but with the MDF extension. And they were just asking, is that correct? And I don't even know personally.
Okay, so
if it matters.
Yeah, it doesn't matter. You could call your files .pol for all SQL Server cares, and that's a very good name to call your files, because pol is a good name. Yeah, it doesn't matter. Just it's generally accepted practice that there's only one MDF, your main data file. There's one LDF, your log file, and everything else is called .ndf. And I can't remember what the N stands for, but it's basically secondary data files. And SQL Server could care less what you call them. But just for the sake of not confusing your DBAs and your other developers, I wouldn't call anything else a .m for Michael DF. I would use N for November instead. Okay.
Here's an interesting question too. Would snapshot isolation help reduce the insert point hotspot in a clustered index when an ever-increasing key problem? With an ever-increasing key problem.
Simple answer, no, because snapshot isolation it does two things. First of all, it provides you with a point-in-time view of particular query results, and the second thing it does is it stops readers blocking writers and writers blocking readers. If you have two writers, they both need to acquire exclusive blocks, and snapshot isolation doesn't help in any way whatsoever there.
Okay. We can go on if you like.
If there's more, I can take more questions. We have plenty of time. We can go for another 40 minutes, and I've probably only got another 20 minutes worth of stuff to talk about. So if there's more questions, let's just do them now.
Sure. Okay, let me scroll up quite a bit here. Here's a question about CX packet. Could you ask my question related to the thread working distributing to avoid CX packet?
I'm not sure.
I'm not sure what that means.
Okay, so whoever asked that question, I'm about to talk about CX packet weights. So Wakeslab talked about CX packet weights and explained exactly what they are. And if you still have a question, ask another question. Okay.
Great. And here's another person. They want to know about the EXEC sync weight type. Execute, I guess, sync type.
Okay, so the exec sync weight type, you can kind of think of it as similar to a CX packet weight. I generally filter out, if we look at my list of things, that's actually a good reminder because I didn't talk about this. This is one of the weight types that I actually filter out because the vast majority of the time it's benign and it's not a performance issue. Okay, but you can think of it as related to parallelism happening. The reason to filter this out, again, it's not usually a problem, and if I've got parallelism happening, it's going to show up as CX packet weights rather than exec sync. So just to kind of dovetail into that, I mentioned earlier on in the deck that there are some weight types that I generally filter out, and most people that do weight statistics analysis filter out because they're not a problem in general. Big generalization. I'm not saying they're never a problem. I'm saying that 99.999 times out of 100,000, then not a problem. And you can see this list all these different weight types that I generally filter out. Okay, and there's the example that I gave here, lazy writer sleep. Now, this code will work on all versions from 2005 onwards, and so will the waiting tasks script. But you can see there that there are weight types that are not in 2005. For instance, this is to do with indirect checkpoints in 2012. This is to do with the query data store that Connor announced at PASS last year, and is going to be in the next version of SQL Server. This stuff still works on 2005 because this is just a textual match, okay, against the name of the weight type. If the weight type doesn't exist, it can't possibly match. Okay, but you can see there's a lot of stuff that gets filtered out. Okay, all right, Rob, Karen.
Okay, I think we're pretty much caught up. I've scrolled through a lot of the questions, and most of them we've answered. And if I missed a question, I will definitely. I'm just going to send you the questions in an email, and I think we hit most of them. So thank you.
Okay. Yeah. And at the end of the session, if or when you're looking at the deck afterwards, if you have a question, then right at the start of the deck, my email address is there. You can send me a question, and I'll answer it for you. Okay. All right. So let's go ahead and stop our test running here. Okay. So those all magically disappear, and get rid of this guy. All right. Back to the slides. Write log waits. So this is waiting for a log buffer or a log block stored in a log buffer to be written to disk. Okay. Now, I don't have time to go into all of the intricacies of how this works, but maybe later on in the year or maybe early next year, I can come back and do one on transaction log performance, and I will explain it in depth in there. But what this basically is a thread is waiting for some stuff to be written to disk. Okay. And the write log wait shows up very commonly on servers because the transaction log often is a bottleneck on systems, and there's often not very much you can do about that. Okay. The one knee-jerk thing to avoid doing is do not create extra log files. SQL Server will never ever write out log blocks in parallel to multiple log files. It only ever writes serially. So some of the things I would do to further diagnose logging waits. You can't tell from the write log wait what the database is that's affected because there's no resource that shows up. So you can't tell which database it is. So what I would do is I would go and look at this guy, DMO.io virtual file stats that I mentioned earlier, and I would look at the output from that and see which of the transaction log files look like they've got high IOs, because this could give you an idea of which of your databases is doing an awful lot of logging writes. Okay. Another thing I would look at is the average disk write queue length for the log drive. Okay. SQL Server has an internal limit on the number of concurrent asynchronous log writes for any particular database. Up to and including 2008 R2, that number is 32, and from 2012 onwards, it's 112. And if you look at the disk write queue length for the physical disk that your log drive is on, and you're seeing that number hitting, depending on which version you're on, 32 or 112, then you've hit the internal limit for what's going on in terms of log flushes. And there's a few things that you could do to try and work around that. I've got that on the next slide. Okay. So the simplest thing to try and alleviate write log waits is to put the log onto the fastest portion of your I/O subsystem. That could be a RAID array of SSDs. Now, I'm very carefully not saying just put your log on an SSD, because if you use a single SSD, you're using RAID 0, and you shouldn't do that. Okay? So you need to have two SSDs and at least RAID 1 between them. And if you have an SSD that internally splits itself up, for instance, like a Fusion I/O card does, you can't use RAID 1 over those two half portions of the card. Okay, you're doing it wrong, because who's ever seen half of a card fail? No, the whole card fails. So you have to have at least two SSDs and RAID 1 across them. So that's the simplest thing you can do. The next thing you could do is you could kind of go against all of our SQL Server ingrained knowledge and make your transactions longer. Okay. Usually you're trying to make your transactions go as fast as possible, but as fast as possible means whenever a transaction commits, the last log block has to get flushed out to disk before the transaction can commit. If you have lots and lots and lots of concurrent, very tiny transactions, you're going to be doing lots and lots of very tiny log flushes, and so you might hit that 32 or 112 limit in the number of concurrent log flushes. Making your transactions longer can try and work around that. Very much easier said than done. Okay. You could remove anything that's creating log records that don't need to be there. For instance, any unused non-clustered indexes or duplicate non-clustered indexes. Anytime you do an insert, update, or delete into a table, you have to do an insert, update, or delete into all of your non-clustered indexes, leaving out filtered indexes, of course. That, if those non-clustered indexes aren't being used, is a bunch of extra log records that don't need to be there. Okay? You could have a GUID cluster key, and you haven't coped with that using fill factors, and so you're doing lots of page splits. Page splits create a lot of extra transaction log, and so on and so on and so on. Okay. If there's none of these things that you can alleviate or do to try and alleviate the number of log flushes that are being performed, and you're hitting the 32 limit or the 112 limit, if you're hitting the 32 limit, you could try upgrading, because then your limit becomes 112. If you're hitting the 112 limit, then really all you've got left is sharding, splitting your workload up over multiple databases or servers, because there's nothing else you can do to work around that 112 limit. Okay. Now, saying that, there is a new feature in 2014 that you could use, and it's called delayed durability. And that could actually help you if you have write log problems, or if you're hitting the 32 or the 100. Well, you won't be hitting it you won't be hitting the 32 limit because you're on 2014. But if you're hitting the 112 limit on 2014, you could use delayed durability. And I'm going to show you an example of that right now. So now let's look at slow transaction log. So what I've got plugged into my laptop is a USB key. And I've got two demos I'm going to do. The first one is just showing you the difference between your log on a slow portion of the I/O subsystem and your log on a faster portion of the I/O subsystem. So let's go ahead and set up our system here. So my slow log is on H column. So I go ahead and set this up. And then I'm going to create just a random table with, I'm not going to create a random GUID key, but I've got a sequential GUID cluster key, and I've got another non-clustered index on C2, which is a date time column. So I go ahead and run that, like so. I'm going to zero out my wait stats so I can show you what's going on in my contrived demo. And then I'm going to fire up my threads, so 200 concurrent connections. Okay, so going back over to Management Studio, if I look at waiting tasks, write log. Okay, so I've got lots of threads waiting for the log to be written out. If I hit F5 a few times, then I'm going to see some write logs I'm going to see write logs mixed up with page latches, and so on. But basically, we're coming back to lots of logging waits. Okay. And if we scroll across, we don't get anything that's going to tell us, okay, always what's going on. Okay. So we do see the database ID there, right, but you might not be able to pinpoint, which of your database files, which of your log files has an I/O performance problem. Okay. The only way you're going to be able to do that is from looking at I/O virtual file stats, like I said on the slide there. If we look at wait stats overall, we can see that while this demo has been running, our write log is our most prevalent wait. Now, either way, either approaching wait stats from the waiting task point of view or from the wait stats point of view, I would see that the log is an issue. Because here, I'm seeing that my average wait time is 24.7 milliseconds. Okay, and that is a very poor write latency for a log file. Okay, so I'd figure out exactly which log file it is, and I'd take some corrective action. In this case, what I'm going to do is I'm going to move the log to a faster portion of the I/O subsystem. So I'm going to go ahead and stop my test. Go back into Management Studio here, and I'm going to comment this guy out and uncomment this. So now I've got the log on one of the other SSDs in my system, and I'm just going to hit execute to create this entire thing. In this other window, I'll flush out my wait stats so I can show you a comparison. Okay. And then I'm going to start up my 200 concurrent connections again. Okay, back to Management Studio. we look at waiting tasks, we're not seeing a huge amount of write logs. And when we do see write logs, they're very small. Okay. Now, occasionally you might see big write logs, but that's when the log is having to grow. Okay. Generally, we're not seeing a lot of big write logs anymore. And if we look at wait stats, okay, now what we're seeing after we made that performance change is write log has dropped down. It's no longer the most prevalent wait type. Okay. And each of the write logs is for 2.3 milliseconds compared to 24.7 milliseconds before. So a very simple change there, moving the log to a faster portion of the I/O subsystem, had a profound effect on the write log wait itself and where it appears in the list of all the waits that are occurring. Okay. So now we're back to what looks like more of an insert hotspot. Okay, so if we hit F5, now we're back to more of an insert hotspot case that I showed you in the first one. Okay, because we have very small clustered index rows here, right? And we've got them in sequence. So a new sequential ID is going to create GUIDs in sequence. So now we've got another hotspot case. Okay, so there's another interesting case that we just looked at there. Now, let me show you delayed durability in 2014. So I'll go ahead and stop that test. Get rid of that. And now delayed durability. So what I'm doing is, again, I'm using the slow I/O subsystem. It's take a little bit longer to create because I'm having to zero out 64 meg on this slow USB key. And then what I'm doing is I'm specifically turning off delayed durability. And I'm creating this scenario with a very small table. And I've got 3 rows in my table, okay, with the values 1, 2, and 3. And what my client is going to do, each of these 50 clients is going to basically do update bad key table set C1 equals C1 plus 1. So each of the clients, the first one to get in is going to do xlock, 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 and then have to commit. All the rest of them are going to be waiting to get an xlock on this one. So essentially, I'm going to have a bottleneck, which is my workload, where only one thread at a time can be locking this. And so the locked are not going to be released until the log block for the commit has flushed to disk. Then the next one can get in. Okay, so if I go ahead and create this scenario, oops. Did I run the whole thing? Let's go ahead and just reset that, like so. Okay. So if I'm going to set up 50 clients, but I'm going to use perfmon here. So let's start it running first of all. I'm not going to look at wait stats, so I can just start the test running. So add 50 clients. And then in perfmon here, I'm going to add in, for my instance, I'm going to add in the log flushes per second and hit control transactions per second for my slow log file database. Okay. And what we're going to see is here's our data coming in. So log flushes per second, and I'll highlight that by hitting backspace, which is going to highlight it in black. So we're seeing about 1,400 flushes per second, 1,300 to 1,400 flushes per second. If I look at transactions per second, it's the same line, okay? Because transactions cannot proceed until the previous transaction has committed, which involves flushing to disk, all right? So my log is a bottleneck here. Now watch what happens when, over here, I turn on delayed durability. Check that out. Wow. Okay? The black line is transactions per second. Okay? So what delayed durability does, it says when a transaction commits, it doesn't wait for the log block to flush. The log block will not flush out to disk until it reaches its maximum size of 60K. So now what we've done is we've actually disconnected the transactions per second from the log flushes. And our log flushes per second has dropped right down to about 250 or so a second. And our transactions per second has jumped from 1,400 up to about 5,000 per second. Now, delayed durability, there is a catch, and the catch is the log block doesn't flush to disk when your transaction commits. So you're told that your transaction has finished even though it's not durable. So no longer do you have the durability guarantee that you had previously. So if you have a zero data loss service level agreement with your business, you should never turn on delayed durability, because if a system crashes, you run the risk of having a transaction that has been told, yes, it's durable, but it isn't. Okay? And that even extends to synchronous mirroring and synchronous availability groups. Even if your transaction commits, you've got delayed durability enabled, and you're using a synchronous mirror or a synchronous availability group, the transaction's not there on your synchronous mirror or your synchronous replica. The synchronicity is only when the log block on the principal or primary gets written to disk. Right? However, if you do have allowable data loss, then you can consider turning this on. Right? Now, I suspect that even people that are not allowed to have any data loss at all will still end up turning this on because of the profound performance effect it can have if your workload is able to make use of it. Okay? So that's delayed durability in 2014. All right. So any questions about the demo that I just did?
Okay, let me take a look here.
And I'll wind things down.
Durability in a ODS, DW, OLAP work environment. Oh, let me back up. Questions kind of run together. Would you recommend a delayed durability in an ODS, data warehouse, OLAP workload environment?
There is no answer that I can give anybody saying, should I have delayed durability turned on? It depends on whether you are able to allow any data loss to occur in your system, and whether the delayed durability is going to have a good effect on your system. Okay, and I can't tell that until you actually turn it on, unless I know specifically what your transactions are doing on all the tables in your system. So it really comes down to the number one thing is, are you allowed to have any data loss? If the answer is yes, you might consider turning it on. Then it is, if you turn it on, does it have any performance effect? If the answer is yes, leave it turned on. If the answer is no, I would turn it off, because I would only have things turned on that I'm actually making use of. Okay, but again, the number one thing is, am I allowed to have any data loss? And if the answer to that is no, you should not turn on delayed durability.
That makes sense to me. Backing up the transaction log every minute could increase log write wait time, and that's what they wrote.
Is that a statement or not?
It just has a question mark following
okay.
it. So
the only thing that backing up the log does, there's a couple of different things that could cause a performance issue. Number one, when you're backing up the transaction log, the log cannot clear, so it can't be reused. So if you have an incredibly high log generation rate, you have a very small transaction log, and you're doing very frequent log reads essentially, right? When you're backing up the log, you might see some log growth occurring. And when log growth occurs, then all the other threads can't write to the log, and it has to wait. That's a very small niche case, though. Most people don't have very tiny transaction logs. The other thing that happens is when you're doing a log backup, the backup system is reading from the transaction log. Now, depending on the amount of write I/O that's occurring and the performance capabilities of your I/O subsystem, the fact that you're reading from this file at the same time as you're trying to write to it, the number of disk heads that you have and so on, you might run into contention at the I/O subsystem level. And so you might see an increase in the write latency while you're actually reading from that file as well. Okay? But again, that would be a case where the I/O subsystem doesn't have very good capabilities for a single read thread to be able to noticeably affect what's going on with write threads. So yeah, the answer is potentially yes.
Okay. I'm going to back up with this question because they asked it really early on in our presentation and I missed it, and they asked it again, so I'm going to ask. So they have a 6-core system with multi-threading on. How does he assure the workload is distributed across and crosses all threads and limits CX packet as one of the top wait types?
Okay.
Hope I said that right.
No, you did. Yeah. We are just about to talk about CX packet weights. Okay, so the only thing you can do is you can make sure that your queries, if you can make sure that queries that are running in parallel are the ones you want to be running in parallel. That's basically what you can do. The distribution of threads across processors, there's nothing at all you can do. SQL Server does that itself. So let's move on to talking about CX packet weights and explain what those are. Okay?
Okay, great. Thank you.
Cool. Okay, so parallelism. So parallelism is where one or more of the operators in your query plan has the need for multiple threads. And so you'll see, for instance, some operators that are using parallelism. And this is an example of one. This is called a repartition streams operation. And this is where you've got data flowing in from the right-hand side, because when you're looking at a query plan, generally data is flowing right to left. You've got a parallel operation that is flowing information into a repartition streams, and the repartition streams takes all the information from the parallel threads and divides it up again in some other way to some more parallel operations. Okay. So for instance, in a repartition streams operation, we're going to see a control thread. All parallel operations have a control thread, which is thread ID 0, and then some producer and consumer threads for this particular parallel operator. So if we're running degree of parallelism 4, we're going to see our control thread, 4 producer threads going into our exchange operator, going out to 4 consumer threads. Okay, so the most number of threads you're going to see for each individual parallel operator in a query plan is degree of parallelism times 2 plus 1. Okay? So when parallelism occurs, you're going to see CX packet weights. And CX packet weights, their basic form just says you've got parallelism happening. Okay? If you have any other thread apart from thread 0 waiting for CX packet weights, that says you've got a problem. And if you've got CX packet weights accruing very quickly, you've got lots and lots and lots of parallelism happening, that might be a problem depending on what you know about your workload. Okay? So the knee-jerk response is set max DOP to 1, turn off parallelism. It's a horrible, horrible thing to do. Sometimes you have to do that. For instance, if you're running SharePoint on SQL Server, you're not supported unless you turn max DOP to 1. In fact, the later versions of SharePoint will stop the installation process unless max DOP is set to 1. Okay? So other things you can look at is have a look, as I'm going to show you, and see what the thread ID is that's showing CX packet weight, and that will become apparent after the next few slides when I explain more about what CX packet weight is. And then have a look at the query plans themselves to see, do you expect there to be parallelism here for this particular query, right? You could also look and see whether there's a pattern. For instance, CX packet weights with page IO latch share weights. That implies you've got a table scan going on. And then go back to a few more slides back when I talked about page IO latch weights and see whether you should actually have a table scan going on. So an example of CX packet weights. You've got a table that's going to be scanned, and the query processor is able to divide the work equally amongst the 4 threads that we've got in our DOP4 system. So we've got 5 threads. We've got our control thread, thread 0, and we've got our 4 worker threads, if you will. Each one is going to scan a quarter of that table. Now watch what happens. Watch the black arrows that appear. They all stop at the same time. If I pull them all back together, okay, thread 0 in any parallel operation always accrues a CX packet weight for the length of the operation. Okay? So CX packet at its basic form is parallelism's happening. Now here's a case where we've got a skewed workload, where the amount of work given to each thread is not the same. Okay? So look at our threads again. Watch the black arrows. Thread 4 takes a lot longer than the other threads, okay, because it has more work to do. Pulling all those threads back together, thread 0 accrues a CX packet weight for the length of the operation. If any other threads finish before the longest running thread, they also accrue a CX packet weight until the operation is finished. And this is where CX packet weights can start to add up really, really, really fast. Okay? If you have unbalanced or skewed workloads where the non-coordination thread is also accruing a CX packet weight. So that's one of the key things to look for. Are any threads apart from thread 0 accruing CX packet weights? Okay. So the CX packet weights, it could just be parallelism. Okay? It could be parallelism you don't want, because you've got, say, missing non-clustered index, or you've got implicit conversions or something like that. Or it could be some kind of statistics problem which is causing a skewed work distribution. Now, some of the things that you can do around CX packet weights, okay, and there's no always right thing to do. Make sure that your stats are up to date so that you're not having any kind of skewed work distribution. That's the number one thing. Okay? You might consider, if you've got one query that has parallelism issues, you might consider using max DOP for just that particular query, okay, rather than setting max DOP for the entire server. If you absolutely want to set max DOP for the entire server, then if you're running NUMA, which most of you are out there, then you can consider setting max DOP to the number of physical cores on each NUMA node, okay, so that the SQL OS system will try to distribute the threads for a parallel operation just within one NUMA node, rather than across various NUMA nodes, to avoid things like foreign memory accesses that are really expensive. No, I don't have time to answer any questions at all on NUMA. If you have NUMA questions, send them to me afterwards rather than asking Rob. Okay. If you're going to set max DOP for the entire instance, be very careful if you have mixed workloads, which many people do, where you might have some kind of OLTP system that's not going to use parallelism, but you've also got reports that run. Then you do want those to use parallelism so they run faster. If you lower max DOP, you might be hobbling that reporting workload. If you're on Enterprise Edition, you can consider using Resource Governor, where you might define a workload group for, say, OLTP that has max DOP set to 1, or max underscore DOP, I should say, set to 1, and another workload group for, say, reporting that has max underscore DOP set to, for instance, 8. Now, what can be even better than changing max DOP at all is changing this thing called the cost threshold for parallelism. And that's a number that the query optimizer uses to decide whether to create a plan that can be parallelized or not. The number is set to 5. Okay? And what you can do if you've got parallelism that you don't want to be happening is bump that number up. Consider setting it anywhere from, say, 25 to 50, okay, to stop little tiny queries that you don't want to start going in parallel from going in parallel. Okay? So there's all kinds of different things you can do around parallelism, but don't knee-jerk and set max DOP for the entire server to be lower just because you're seeing CX packet weights. And I'll show you an example of just that particular problem right now. So let's look at parallelism. So what I've got here, a lot simpler demo, I've got a script called parallelism.sql. Now I've got a database, and you'll have the setup script here. It creates a database with 100,000 rows in it. Each of them has 1,000 columns with random columns populated with values. It's supposed to simulate some kind of document management system like SharePoint, where you might have a large number of attributes for each of the rows, where not all the attributes are populated in each of the rows. So if we have a look here, what I've got is my script. It's going to look at all 1,000 columns. It's basically going to pick a random column and do a select top 10 based on that particular column. Okay. So let's flush out let's get rid of this. We don't need this anymore. Let's flush out my weight stats here and set this going. So this is running DOP 8. Okay. And what I've also got is I've got set statistics time enabled, so we can see how long each of these executions takes. Okay. And what we're seeing here is about a second, about a second, about a second, okay, for each of these with DOP 8. Now if we look at what's happening with waiting tasks, let's get some parallelism. Let's get a few more threads. There we go. So here's an example of parallelism happening, where I've got my control thread, thread 0. These are all for the same SPID. I've got my control thread with a CX packet wait. I don't have any other threads waiting for CX packet, so I don't have any kind of skewed word distribution. I have some of the other threads waiting for other stuff, and that's perfectly fine. One of the things you might see commonly with table scans occurring is other parallel threads waiting for latch access to this guy, access methods dataset parent. So this is a data structure in the access methods portion of the storage engine, and this is the dev team that I used to run back at Microsoft. And this is a data set is essentially, you can think of it as encapsulating a scan. It's an object that encapsulates a scan. And so this latch access methods dataset parent is where a thread has finished checking the stuff it's been given, and it's calling back in saying, hey, what's the next thing for me to be given? What's the next thing for me to be given? Okay. Now for the CX packet wait type, you can see that it's blocking itself. Okay, it's waiting for these other threads to finish. Now the other 6 threads here are obviously working on different schedulers, and they're not waiting for anything right now. If we go ahead and look and see where the parallelism is, you might have a query plan that has 1,000 different operators in. Okay, using this script, you can see which of the nodes in your query plan that CX packet weight is actually coming from. So this is node ID 1. If I go ahead and look at my graphical query plan, obviously this is a very simple example. Node ID 3 down at the bottom there, node ID 2, node ID 1. So there's the parallelism happening. Okay, so you can go and figure out in a larger query what's going on with your parallelism. Now if we look at wait stats, we've got CX packet weights. So I'm going to knee-jerk and say, oh my goodness, we've got CX packet weights occurring. Let's lower the DOP, see if we can get rid of them. So I'm going to stop this query running. And we all saw that it was taking about a second or so for each of the executions to run. And I'm going to lower DOP to 2. Okay. I'm going to flush out wait stats in the other window first. And then I'll start this running with DOP 2. And we're going to see what goes on in terms of the wait statistics that we see and also the query runtime that we see. So we go across to my messages. Now we're seeing that the queries are taking 2 seconds, 2 seconds, 2 seconds, 2 seconds. If we look at our wait stats, okay, we still have CX packet weights because we're running DOP2, but we have a lot fewer of them. But if we look and see how long they're taking, each individual one is now taking 500 milliseconds, whereas previously they were 100 milliseconds. So I've reduced the number of CX packets weights that are occurring in my knee-jerk reaction. However, each CX packet weight is now longer, and each individual execution time of that query is now longer. So parallelism wasn't an issue here. Parallelism was actually good in this case, and I shouldn't have reduced any parallelism. Okay. Now, we've only got 5 minutes to go to the end, so I'm just going to run through the last few slides, and then we'll take questions for whatever else is left. Okay. I've just got a few more slides to go. So async network I/O wait. 3 more wait types, and then we're done. The word that you fixate on in the name of this wait is network. Okay, a very common knee-jerk reaction is, oh, it must be a networking issue. This wait type should really be called SQL Server is waiting for your application to acknowledge that it got the data that was sent to it. That's all that wait type is. Okay. The vast majority of the time when you see this wait type, it's from poorly written applications doing what's called rebar, row by agonizing row processing. For instance, SQL Server sends it some data, and it looks at the first row, does some processing, displays it. Looks at the second row, does some processing, displays it. What it should really be doing is cache everything that SQL Server was sent and say, okay, so SQL Server goes off and processes some more, creates some more data. The application, in the meantime, is processing away, displays all the rows. By the time SQL Server comes back with the next set of information, the application has processed all the data and is waiting for the next set of data. That's a much better way of doing it. But a lot of applications out there just do 1 row at a time processing, which means SQL Server can't make any more progress. This is very easy to demonstrate. Get a large table on a SQL Server, go onto the server itself, Management Studio, do a select star, and you'll see async network I/O waits. Because Management Studio is a poorly written application that does rebar row processing. Now, it could be a network issue. Most of the time, though, it's not. If you think it's a network issue, measure how long it takes to ping between the server that's running the SQL Server and the server that the client code's running on. And you'll find most of the time that the ping time is an awful lot less than the average async network I/O time. Okay. OLADB, we already talked about that. The knee-jerk reaction is that it's linked servers. Nowadays, generally, it's not. Okay? It's going to be a third-party monitoring system running DMVs, or maybe something that you've done running DMVs over and over. Could also be CheckDB, because CheckDB uses OLADB internally. If the average OLADB wait time is tenths of a millisecond or a millisecond, it's not linked servers. If the average time is tens or hundreds of milliseconds, it's going to be linked servers. And how do you debug the linked server? If it's a SQL Server, you go across and do wait statistics analysis. If it's anything else apart from SQL Server, I have no idea how to do that. So preemptive waits. I mentioned that if SQL Server has to call out to Windows, the thread that calls out has to switch to be preemptive. So a preemptive wait is one where the thread's called out to Windows. So these guys are basically not documented at all. Okay, one more reason that I'm going to do my kind of library of wait types. What you can do, though, is, for some of them, is take off the preemptive _OS_ and you're left with something. Take that something and search for it and MSDN in Google or Bing, and you'll find the name of a Windows API, hopefully. Okay? That doesn't work for anything ending in ops, like pipe ops or file ops or crypt ops, because those are kind of catch-all things for a large number of different Windows APIs. But that might give you an idea of what the API is. Okay? Now, for instance, if you're seeing preemptive OS, cryptops or get auth or get authentication or something like that taking a long time, that's SQL Server calling out to a domain controller or an Active Directory controller to try and get some security information. How do you debug that? Go and figure out what's taking up the time on your AD or your DC. Okay, so you're going to have some kind of system admin go do that for you. So to summarize, the methodology is going to be, before you even look at wait statistics, okay, ask the people, when did the problem start happening? What are the symptoms of the problem? And what did you change? And after they've told you, I don't know, we didn't change anything, start looking at wait statistics. Okay? So DMOS waiting tasks, what's going on right now? DMOS wait stats, what's been happening in the past? The output from DMOS wait stats, you're going to look at the top 3 or 4 relevant waits. Okay? If you see latch underscore, you're going to have to go and look at what's going on with latches. Okay? And there's a DMV to go and look at that, and there's a lot more information on my blog or in the Pluralsight course for how to do that. So figuring out what those top 3 or 4 wait types are, understanding what those mean, and where to go digging for more information. Don't just knee-jerk, for instance. You see write log, so you add another log file. Or you see CX packet wait, you turn off any kind of parallelism. All right? Lots and lots of more information you can go and figure out what's going on under the covers. So some resources. There's an old white paper that talks about weights and queues, which is the original name for weight statistics analysis. It's from 2006. That's like almost 9 years old now. It's old. A lot of the information's out of date, and it's by no means complete with anything after 2005. If you want to go a lot deeper, stuff I haven't talked about today, there's some white papers here that I helped to write for the SQL team about latches and spin locks, and I also talk about those in the Pluralsight course. There's a new white paper that Jonathan and Erin wrote in concert with Redgate last year, and that's available on our website here. This is more of a, here's how to get started using weight statistics, here's a bunch of scripts, and so on and so on. And then I have an awful lot of stuff on my blog about weight statistics, latches, and spin locks. So with that, we've been going basically just on 2 hours with questions. Any more questions? Do we have some more time for questions, Rob?
Yeah, we're really running short on time now. So what I'm thinking about doing, if that's all right with you, is just forward the questions to you, and at your leisure you can respond back. Is that all right?
Yep, that's fine. I can maybe do a blog post or something with generic question answers in.
And we're getting a lot of thank yous. Great jobs. In fact, we had I don't know if it's been the most people log in today since I've been doing the webinar, but we had over, I think, 220 people come. So I want to thank everyone for
cool.
joining our webinar. Thank Paul for giving the webinar. And once again, if anyone wants to talk at one of these webinars, just email me. My email address is rob@sqltigers.com. I'd love to have people talk at our webinars. And I can't thank Paul enough for spending 2 hours today and giving a great presentation.
No, you're very welcome. Thank you for having me.
And last thing to say, the webinar is recorded, and it will be on the PASS website as well as my blog. And I will get all the scripts, etc., whatever Paul provides me, and post it there too, so everyone can download it and access the webinar. So I guess we're just going to shut it down now. And once again, thank you, Paul. And I hope everyone has a great evening. Thank you again.
Thanks. Bye-bye.
All right, bye.